Okay, good morning everyone. Dr. Nat here. We are continuing with module number 10. Oh, this is part 2, but we're doing a recap first. So module number 10, we've talked about it last week, right? We talked about the fundamental sampling distribution. So let me write that somewhere. Draw. So there were 3 components to module number 10, and we talked about the first one, which was the fundamental sampling theory. This is recap, okay? Fundamental sampling theory. Right. So we talked about population, which was just repeating.
Sorry, doctor. Are you presenting slide right now?
Yes.
Because we can't see what you're writing.
Oh, okay. Thank you for letting me know. Not sure what's going on. Let's see. Oh, shoot. Okay, can you guys see this one? Yes or no?
Yes, doctor.
Okay, great. Not sure what happened. Oh, this is always happening. Okay. Thank you. All right. So we are doing a recap first, as usual. So we are discussing about the fundamental sampling theory. Okay. Can anyone tell me what's the difference between population versus sample? Easy question.
Population is like whole data, while sample is the subset of population.
Correct. It's the whole data itself, or you can say total observation, same thing. Whereas sample is the subset of this observation. And then population, can it be infinite or not?
Yes.
Yes, it can be infinite. We saw this example when we were discussing about data collection that was ongoing every day. So you don't know when the end of the world is coming, right? So if it's every day, so meaning to say the data is going to be infinite. There's always going to be more data to be collected. So it can be infinite and it can be finite. What about sample? Can sample be infinite? Can sample be infinite? Oops. I just kicked my lamp. So anyone? So can sample be infinite or not? No idea? Okay, so sample is always finite because you always have this number n. You always know what n you're taking because it is a subset. You're taking a small chunk out of the population. It has to be some number, and therefore, if you know what the number is, it is a finite size. Finite size meaning to say you know the number. And then what else can we talk about? Finite with n size. Finite with n size. Oops, okay. And then we talked about, so these are the difference between population and sample. So these are total observation and this is a subset, easy stuff. Okay, so we're done with this one. We're gonna use this knowledge later. So now we're talking about independent random variables. Yes. Finish what? Okay, nah, you want more? Come, nah. So mommy is teaching. Can you take this bread and go? Okay, sorry, advertisement. Right, bread advertisement to be specific. So let's continue with independent random variable. And this is also not new to us. Does anyone remember what this is? What makes a random variable independent, which is very important? What makes it independent or simple? So if I have x1, x2, up to xn, we're talking about random variables. What should the characteristic of my random variable have? They should have equal chances of being selected, right? They should have equal chances of being selected. I cannot pick random variables that I know that I'm going to choose x3 all the time. So that is not an independent random variable. So when I choose data or when I choose a sample, I need to make sure that this is not biased in any way and they all have equal chances of being selected when I'm doing my experiment. So that is your independent random variable. And then what else did we talk about? This, because of this, they have equal chance of being selected, which means that they would have no bias. This eliminates the bias. And we also talked about, we also recapped on this one, which is mu x is the summation of x, whereby x times with the probability or the PDF. And this was in module number 6, I believe. So this tells us the mean for population. Mean for population. And then this one would tell us the variance or the standard deviation for a population. This would be x squared, px, and then minus mu x squared. So very, very important for you to identify that this is the mean for population. If I tell you that it is a sample, do not use this one. Do not use this equation. This is specifically for population and this is for discrete. If you're talking about continuous, it is the integration. And for variance, you have the alternative equation. It's in your notes, please look at it. And these types of equations are considered easy, so they won't be provided to you. Only the distributions will be provided. So please remember to memorize these equations. Okay. I'm not saying they are easy, but they are considered easy for mathematicians. Okay. And
Hashim, bagi Hashim.
okay, bye-bye. Now take tissue. You don't come in, okay? Okay, so now we're going to talk about central limit theorem. If you guys still remember what that is. New slide. Sorry, my kid is sick, so he's not at school. Therefore, the interruption. Okay, so central limit theorem. Okay, so this is a new one and supposed to be interesting. What was the number that we talked about that gives us a good approximation for a sample to be normal, to have a normal distribution? Anyone remembers? What was the N? 20? No one remembers? Okay, because I did not upload this lecture on the Putra Blast yet, so I know. So the number is 30. What did central limit theorem tell us? It told us that despite the population not being a normal, the population does not have to be a normal. It can be normal, it cannot be a normal. So whenever you have a population and you get the sample from this population, if your data, if your sample size is greater than 30, you would always get an approximately normal distribution, even though your population is not normal. So we're going to continue on this part. So if you have any questions, you can ask me. Recap. Okay, so last time it was slightly different. I changed the definition to make it easier. The last definition was a little bit complicated. Okay, so the central limit theorem, let x1, x2 up to xn be a random sample from a distribution with mean mu and variance of this guy. So this is from a distribution. So this is a population with mean mu and variance. Remember we talked about this one and this one. So this was from the population and we can find it. If we can't find it, sometimes they give it to you. So if n is sufficiently large, and the large here means more than 30, your sample mean has approximately a normal distribution with mu of sample mean x equals to mu, which means that the mean is equal to the population mean, and your variance of the sample mean will also, the variance of the sample will also be equal to your variance of your population divided by your size of n. And then we have a new term here, which is T naught, also has approximately a normal distribution, which is mu equals to n mu. So this is the population mean times with the size. And this is the variance of T naught, which is equal to n times the variance of the population. So what is T naught? T naught is, last time we defined it as the sum of sample. Sum of sample. Don't be too worried about this one. Make sure you understand this part though. Okay, so I'm going to erase that so it's not going to appear on your lecture note. Okay, so for most population, if the sample size is greater than 30, the central limit theorem approximation is good. So let's look at this diagram. The central limit theorem shows that if this is the population distribution, it's not normal. It's not normal, it's slightly skewed, right? It's skewed to the right. And you have a sample of a size n, and they define this size n to be moderate, meaning to say it's not that large. So despite having a moderate n, you can see that the distribution is approaching towards normal. Whereas if you have a larger n, the sample distribution is approximately normal. It looks better. So having a larger n will always give you a better approximation of the normal distribution. So small n, quite okay, like normal, but not the best. But if your n becomes larger, you have the best normal distribution approximation. So this allows us to compute probabilities for sample means using the Z table, because we are lazy. So we want to use the Z table, at least me, I am lazy. So next one, we already talked about this one. And we talked about what happens if we increase the sample size. It becomes a better normal distribution approximation. And the central limit theorem holds for both discrete and also continuous distribution. So this is discrete. This is why you see the boxes here. Whereas if it's a smooth curve, you know it's a continuous distribution. Okay, so from the central limit theorem, it's a very, very important theorem because it is like the basis of many, many other theorems. So from the central limit theorem, we can derive equation that we already talked about before, which is the expected value or the mean of our sample is just equal to the population mean, whereas the variance of our sample is just the variance over the number of n. So if you were to find the standard deviation of your sample, you need to divide it by the square root of n. And most people will make a mistake over here. So take note on that. If you're trying to find the standard deviation, it is the square root of n. So this part is a bit confusing. Most people screw up here. In addition with, this is our sum of sample. T naught is, you just add all of this together, which is just n of mu. And this is what you get. And then the variance is n times with variance. Okay, so number one, what does it exactly tell us? Result number one tells us that the distribution of our sample is centered precisely at the mean of the population. This is what the central limit theorem tells us, right? When we get a sample from a population, it will always be approximately a normal distribution. So when our sample mean is equal to the population mean, this is what we are getting, a a distribution that is centered towards the mean. And result number 2, which is this guy, shows that the X distribution becomes more concentrated about the mean as the sample size n increases. So let's look at this equation again. So if you look here, you can see that if my n is greater, let me write it somewhere here. If my n increases, why am I using a highlighter? If my n increases, right? What would happen to the variance? What would happen to the variance if my n increases?
It becomes
smaller.
It becomes smaller. What is it better to have a smaller variance or a bigger variance?
Smaller variance.
Smaller variance. So if I increase my sample size large enough or very large, my variance becomes really small, which means that it becomes a teeny distribution that is very, very centered towards the mean. And this is what we want because our data is not spread out. So this is what the central limit theorem is trying to tell us. So X, the sample distribution when n is 10 is like this. And the sample distribution when n is 4 is spread out because the variance is bigger. This one, the variance is smaller from this equation. Okay? Any questions about this one? Everyone okay? Right, I'm going to continue.
Okay.
All right, so we already seen this example. I'm just going to repeat myself here. An electrical firm manufactures light bulbs that have a length of life that is approximately normally distributed. So we know that the population is normal. So if my population is normal, by right off the bat, I already know that my sample is going to be normal. Okay, so sample also normal. Doesn't matter what number I have, what number n, because I'm getting it from a data that is normal. With mean equal to 800 and standard deviation of 40. This is 40. So this is population. Find the probability that a random sample of 16 bulbs, so now our n is 16, will have an average life of less than 775. So we are trying to find when the sample size, when X is less than 775. So typically we would write it like this. What is the probability of X being less than something something? So we would write it like this. But for this module, we're talking about the sample mean, right? Sample distribution. So instead of writing it just as X, we need to write it as this guy. And when we have this, it means that we need to apply the Z. We have to convert the values to Z so that we can find the Z from the table, right? Okay, so this is what we already did last time. So I'm just repeating myself here. So this is so remember the definition for sample mean is just mu. And for the variance, it is variance of the population divided by n. This one is standard deviation. So we need to standard deviation divided by square root of n. What was it? It is 40. So 40 divided by square root of 16 is my standard deviation for my sample distribution. Okay, so with that said, I already know my mu, I already know my variance. So now I can find what is my Z value. So 775 minus mu divided by, mu of X divided by, what was this? The standard deviation of our sample distribution as well. So this was the equation for Z. We have learned this in module number 8. We're applying it here again. So mu of sample is 800 and the standard deviation is 40 divided by square root of 16, which is 4. 40 divided by 4 is 10. So you would get your Z as minus 2.5, and just referring to the table, you would know that this is 0.0062. Okay, we're not going to go over the table. All right, so next example. So let X denote the number of flaws in 1 centimeter length of copper wire. Okay, so we are talking about flaws as our random variable for 1 centimeter length of copper wire. The probability mass function of X is presented in the following table. So our random, this is number of flaws, and this is the probability. So for flaws, for 0 flaw, the probability is 0.48. If you have 1 flaw, it is 0.39. And if you have 2 flaws, 0.12. And so you can see that from this distribution that the highest probability is by the no flaw, right? Which is good. Okay, 100 wires are sampled. So N is equal to 100 from this population. So this guy is the population. No, this guy is the population. When we're talking about probability distribution, it is always the population because you have the number of the probability which describes the entire data, right? So that is your population. What is the probability that the average number of flaws per wire is less than 0.5? Average number of flaws per wire is less than 0.5. So number of flaws less than 0.5, trying to find the probability. So what is the first thing that we need to do here? Okay, I'm going to let you guys look at example number 2. What was the first thing that we did here?
We normalize the data.
Normalize the data. How would you normalize the data?
Find the mean and standard deviation.
Find the mean and the standard deviation. Correct. This is what we did first. We found out what was the mean and standard deviation. So first, I need to find the mean of my population and also my standard deviation or variance. So mean and standard deviation of population. Okay, so mean. Remember the equation for mean, it is the summation of all the x's. So 0 times with 0.48 plus with 1, 0.39 plus with 2, 0.12 plus with 3 times with 0.01. And because I'm super smart, I know what this is. I'm just going to look at my solution here. 0.66. So that was the answer. Okay, so this is my mean for the population. And then for the standard deviation, I do the same thing. Summation of x. And what was the equation? It was x squared times with the probability of x equals to some value. Okay, just like that. And then minus with the mean squared. So this is supposed to be the easier equation. I think there's another equation. I don't remember what it is. Okay, so this happens first, and then you subtract it with the square of the mean. So, should I do it? Should I do it or should I not do it? Let me just show you the solution. I already did it. Okay, so find the variance. So this is the equation over here. So 0.39. This is 1 squared, by the way. 1 squared times with 0.39 plus 2 squared times with 0.12. And then 3 squared plus with 0.01. And then you add these together minus with 0.66 squared. Actually, you don't have to have this bracket. It will give you the same answer, but I'm trying to make you guys understand that this thing doesn't happen. This thing is not happening for all the x's. Okay, let me try to rephrase myself here. So if I did not put the bracket, you can interpret this equation to be, let's say 1 squared, 0.39 minus with 0.66 squared for all x's. So this is not the case. You have to sum all of this over x's and then minus the mu. So please understand the equation carefully. Okay, 1 squared. And so this, we get the answer as 0.5244. So this is the find the population mean and variance. Step number 2 is finding the sample mean and variance. So easy, our sample mean is just the population mean, so it's just 0.66. Whereas for our sample mean, it is the variance over n, or the standard deviation over square root of n. So this is what we get. Our n is 100. Okay, what's the next step? We already found the population mean and variance. We already know what is the sample mean and variance. What is the next step?
Find Z.
Find Z, correct. So find Z value for x that is less than 0.5. Let me rewrite that. It should be like this. Okay. So just using the Z equation, 0.5 minus the mean that we sample mean that we already got divided by the standard deviation that we already got. And you would get your Z as minus 2.153. If you use the table correctly, please don't make a mistake there. You would get the probability as 0.0136, which means that it is 1.36%. 1.36%. Probability is just percentage, by the way. Only 1.36% of the 100 sample that you selected as your sample will have flaws that is less than 0.5. That was easy, right? Just a little bit lengthy. So first, find the population mean and variance. Second is finding the sample. Third, find the Z. And then you refer to the table as your final step. Okay? Any questions about this type of question? Very highly to be on the test as well. Similar format. Okay, everyone's okay? Okay, moving on. So we talked about sampling distribution for one sample data. Excuse me. What if we have two sample data? No, sorry, not two sample data. Two sample data from two different populations. So if independent samples of size N1 and N2 are drawn at random from two populations. So you have one population, two population, and you get sample from each. They are not the same population. It can be discrete or continuous with means mu1 and mu2 and variances of this guy and this guy respectively. Then sampling distribution of the differences of means x1 minus x2 is approximately normally distributed with mean and variance given by, so this is our mean, it's just mu1 minus mu2. It's quite similar to our mu x equals to mu, right? Except that we have 2. So it's mu sample 1 minus sample 2 is equal to the mu of population number 1 minus mu of population number 2. And then this is the variance of the sample, the differences in the variance. So it is the same equation as well, but instead of a minus, it is a plus. Even though we're talking about the difference, it is a plus because we're trying to find out how spread out the data is. So when you have two population, it is more spread out. So you have to add them together. Okay, very important, take note of this. It's not a minus sign, despite this a minus sign. Okay, hence, if you were to find the Z value so that we can refer to the table, it would be whatever that you're trying to find minus the mean of the differences divided by the variance, sorry, the standard deviation of the differences. Okay, so we're gonna look at an example. Any questions? I heard someone unmute. Are you okay? Any questions? No questions? Okay. We assume that the conditions of central limit theorem apply for this approximation. Okay, so why can we still approximate this as normal? So previously we talked about one population, right? And we said that if we take a sample from a population, it doesn't matter if the population is a normal or not, as long as our sample size is big enough, we know that it follows the normal distribution. So here we are assuming the same case. We are assuming the sample follows a normal distribution. This guy also follows a normal distribution. So when you have two samples that follow the normal distribution, you apply the normal distribution equation on them as well. So this is why we can use quite a similar equation as to the previous one. Okay, so this is an example. Two independent experiments are being run in which two different types of paint are compared. So we have two independent experiments, which means that we have two population. 18 specimens are painted using type A, and the drying time in hours is recorded. So I'm assuming that our variable X is going to be the drying time in hours. X in hours, X1. The same is done with type B. So we're going to call that as X2 in hours. So we have two sample for two population. The population standard deviations are both known to be 1. So yeah, let me get this space. Okay, let me put it over here. Okay, where do we have two? Okay. Okay, so they said that the population standard deviation, so equals to 1, and this is equal to 1 as well. Assuming that the mean drying time is equal for both types of paint. Mean drying time is equal, so mu of 1 is equal to mu of 2. Find the probability that the difference between the mean is greater than 1, where the sample mean of A and the sample mean of B are average. Sorry, this is not a sample mean. This is sampling distribution. My bad. So the difference between these two samples is greater than 1. This is the drying time, right? Our X is drying time. Excuse me. The difference between the drying time between A and B is greater than 1. This is 1 hour, by the way, because we defined our X to be in hours, or at least the question defined it as in hours, where XA and XB are average drying times for samples of size NA is equal to NB, which is equal to 18. Okay. So the first thing that we need to do is find the population, but they already gave us the population. What is the next step? So mean of 1 is mu of 2. This is our unknown. Then mu of 1 is 1. And then mu of 2 is mu of 1. Mu variance, standard deviation of 1 is 1. So I didn't need to write this twice. Let me just. Next one is find the sample. So what is the sample mean? What is mu of drying time A minus sample drying time B? What is the equation for this?
Mu1 minus mu2.
Mu1 minus mu2. So if it is equal, what would be the mean?
0.
0. Mu1 minus mu2 is 0. Is this possible or not possible?
Possible.
Possible because? No idea? Okay, so we talked about the normal distribution having a mean equals to 0. So it is possible. And it is good news to us because it makes our life easier. Okay, great. Thank you for answering that. That is correct. The mu is actually 0. The mu of the differences is 0. And then we need to know what is the sample difference, standard deviation, which is XA minus XB equals 2. What was the equation again? It is standard deviation 1 over square root of n, and I need more space. Let me do that first. Am I going too slow or is this okay?
Okay, Doctor.
Okay. All right, so our equation was plus, remember, plus 2 square root of n. This is for standard deviation. If it's variance, then you square this. Okay, so it is 1 over square root of n, which is square root of 18, plus with 1 over square root of 18. So this would give you 2 over square root of 18 as your standard deviation. Is this correct? Let me see. 1 over 18 plus 1 over 18 square root 2 over 18 is 1 over 9. Square root of 1 over 9 is not the same as square rooting that differently. Okay, so I did a mistake. You have to remember this equation. So if you were to find the standard deviation, it would be the square root of the entire thing. Oh, what's that? N1 over N2 square root. So if I were to do it like this, what was it? Square root of N. It's not the same answer. So I am wrong. I need to use this equation, the basic equation. I cannot use the equation that I use for one population and apply it for the differences between two population, right? So I can't do that. I have to remember this equation and square root the entire thing. Okay, so I already tested it out. It's different. So we have to use the real one. So let me do that again. So this is not it. Okay, so this would be the variance over and square root that. So you get 1 over 18 plus 1 over 18 square root of, this is going to be 2 over 18, which is 1 over 9. And square root of 1 over 9 is basically 1 over 3. Okay, so this is our standard deviation. Okay, so please take note of my mistake just now. Don't do the same mistake. Okay, so we already found the sample. Sorry, this is not the sample. Oh yes, this is sample, sorry. Find the population, done. Find the sample, done. Next is finding the Z. So I'm just gonna go for the solution. So if my difference in drying time between sample A and sample B is greater than 1, so I have to change this number to become Z. So 1 minus the mu of XA minus XB over the standard deviation of the differences between sample A and sample B, which we already found just now. And this would give me 1 minus mean is 0 over 1 over 3. So 1 over 3 is just times with 3. So the answer is 3. Your Z is 3. So use the table to find what is the value for Z greater than 3. Remember, if it is greater, you need to find the value from the table and 1 minus value of table. Because when we're talking about cumulative distribution function, when it is over here and we want to know what is greater than 3, Z that is greater than 3, you want this region. But the table tells you this region. So please take note, it is going to be 1 minus the value of this turquoise region. Okay, don't make that mistake, please. There's 59 of you. Please don't make this mistake, okay? Any questions about this question before we take our break? No questions?
So far, no
Everyone's
question,
okay?
Doctor.
Okay, so let's take our 10-minute break because I talked for a long time. 9, 10. Let's come back at 10. This is 11. 10 a.m. Okay, let's come back at 10 a.m. Go to the toilet, get your coffee, get your water. I'll see you back at 10 a.m. Excuse me. Oh, okay. The lab. Let me text the AutoCAD class. Okay, welcome back. It's 10 a.m. Can you see my chat if I share it here? Or do you not see it? You only see my slide?
I just like
Okay. Okay, so the chat is still private. Okay. Okay, so let's continue. Little bit more to finish part 1. Okay. So far everything is straightforward, right? You just need to remember the equation and the steps and not to make any mistakes when referring to the table. So a lot of interdependent factors there, but I believe you can do it. Just do a lot of practice. Okay, so let's continue with this guy over here. Okay, so we talked about this example here and we discovered that the sample standard deviation for both of paint number A and paint number B has a sample standard deviation of the difference between the drying time of A versus drying time of B is 1/3. We found that earlier on. And the mean between these two drying times is 0. So there is a further understanding of this question. So we found out that the answer for the probability of the difference in the drying time being greater than 1 hour, this is 1 hour. Remember, XA is drying time of paint A, this is drying time of paint B. So the difference between them is 1 hour. What is the probability? And we found out that from our extensive calculation, we found out that the answer is 0.0013. This would mean that it is very, very small, right? So if we were to change this to percentage, we would get 0.13% if we wanted to change it to percentage. So 0.13 is very, very small. Therefore, we can conclude that if we were to look at our normal distribution, that 0.0013 is just like a teeny weeny part of this distribution. So it is highly unlikely to happen. What is the topic in discussion is the difference in drying time. So they are asking you, is it highly likely for the difference in the drying time to be greater than 1 hour? The answer is no, because it is very small. So what if we change this difference and we wanted to find out, is it likely for the drying time between these two paints to be 0.25 hours? Or they said 15 minutes, but we have to convert it to hours because we're talking in hours, right? So we want to find out, is it highly likely for this to happen? What is the probability? Okay, so this question tells us, on the other hand, suppose that the difference in the two sample averages is as small as, say, 15 minutes if mu A is equal to mu B. So they are asking us to find what is the difference in drying time, the probability of the difference in drying time to be greater than 0.25 hours, because they want us to find out for 15 minutes, the average time for drying. Okay, so since this probability is not low, okay, sorry, I need to go over the calculation first before we go to that conclusion. So we already know that we have these values, right? Sorry, this is not the population, this is the difference. So this is what we got earlier, minus XB was 1/3, mu A is equal to mu B, and the difference is therefore 0. So we want to convert this into our Z, because this is our sample value, sample parameters. Next step, this is step number 2. Our next step is to find the Z, right? So Z is equal to 0.25 minus the mean of the difference, A minus XB, divided by the standard deviation of the difference minus xp. So this would be 0.25. So this 0.25 minus with 0 over 1/3. So 0.25 times with 3, you would get your z as 0.75. So referring to the table, you would get z that is greater than 0.75 to be 0.2266. And if we convert it to percentage, it would be 22.66%. So 22 is very high. No, not very high. It is high compared to the 0.13 earlier that we got. This one, right? This was 0.13%. So 0.13 versus 20% is high. So we can say that the probability of the drying time difference between paint A and paint B to be 15 minutes or 0.25 hours is highly likely compared to the 1 hour at least. Okay, so this is what we are talking about when we are trying to find the difference between them. I hope that makes sense. Any questions about this one? So if you have a smaller probability, it is less likely to happen compared to something that has a higher probability. Of course, that is like common sense. So everyone okay?
Nak confirmation, no?
Confirmation?
Untuk yang Z greater dengan N tu, tak payah tolak.
Z greater than
0.2266. Okay, cari dia punya jadual.
Oh, you mean like 1 minus the value of the table?
Yeah.
Yes, this is already 1 minus the value of the table.
Okay, thank you.
If I got it right, let's see. 0.75, Z greater than 0.75. Let's see. Stop sharing. Let me share my module number 8. Okay, need to open that again. Open 8. Okay, share by link. Here's number 8. This one. Okay, so our Z is greater than 0.75. So let's see, where is the table? Table is in module 8. 0.75, so we are talking about positive 0.75. So I'm going to look over here. So this is 0.7. Let me make this bigger. Okay, hopefully I'm not going to make a mistake. So 0. Oh, this is big. 0.75 is around here. So this is 0.773373. So 1 minus, remember when we're talking about distribution, and if we're talking about something that is greater than Z, we need to 1 minus the value of the table. So 1 minus 0.773373. The answer is 0.2266, which is what we got in the slide earlier. Okay, are you seeing this slide or is it not showing?
Yes, doctor, we can see it.
Okay, great. Okay, stop sharing. Share the module number 10 again. What happened? Can you see the further understanding slide?
Yes, doctor, we can also
Okay.
see it.
So this is what we got. This is already 1 minus the value of the table. So we got around 20%, which is higher than the 0.13. Okay, last example before we conclude part 1. And then we're going into part 2 of module number 10. Not done yet. So television picture tubes of manufacturer A have a mean life of 6.5 years and a standard deviation of 0.9. So this is population. So mean life, 6.5 years and standard deviation of 0.9 years. So everything should be in years. While those of manufacturer B, so I'm going to write this as A, and manufacturer B as 6 years and standard deviation of 0.8 years. Okay. What is the probability that a random sample of 36 tubes from manufacturer A, so our N for A is 36, and our manufacturer B has 49 tubes for sample. Okay, so what is the probability that a random sample of 36 tubes from manufacturer A will have a mean lifetime that is at least 1 year more? 1 year more. So they're saying that XA minus XB at least 1 year more. At least. Then the mean lifetime of the sample tubes of 49 tubes from the manufacturer B. So we know that our X is the mean lifetime. So this is what we're trying to find. Okay, probability of the mean lifetime. Okay, so this is what we're trying to find. Same case over here. We need to find out what is the population values. We already have it here. Great. And then we need to find what is our sample values. And our sample values for the mean difference. For the mean difference is XA minus XB equals to mu of A minus mu of B, which would give you 6.5 minus 6. 6.5 minus 6, which gives me 0.5 years. So the mean is 0.5. The mean difference is 0.5. Okay. Next one is to find the standard deviation, the variance. The variance is given by standard deviation 0.9. So 0.9 squared divided by n, 0.8 squared divided by n, and then you square root that. I'm going to use my calculator for that. 0.9 divided by, 0.9 squared divided by 36 plus with 0.8 squared divided by 49. Let me try again. Plus 0.8 squared over 49. So this is my variance. I'm going to square root that to get my standard deviation, and the answer would be, this is me being lazy. So the correct way to write this is like this. 0.1886. Okay. More space. I think this is okay. So now that we have our sample values, the third thing to do is our Z. Okay, fairly easy at this point. We are trying to find this probability. So 1 is our value. So 1 minus mean divided by the standard deviation. So our mean is 0.5. We already know that. So this would be a positive Z value divided by 0.1886. And something that is greater than Z, 1 minus the value of the table. So the probability answer would be 0.0040, just very small. So it is highly unlikely for the differences between the difference in the lifetime between manufacturer A and manufacturer B, the TV manufactured by A and manufactured by B to be greater than 1 year. Very unlikely, very small. Okay, was that easy? I think if we follow the steps correctly, I think it should not be a problem, right? I think I'm going to skip this one first. Save this. What time is it? Okay, so far the part 1 of module 10 is fair game for your exam. Everything that we talked about here, I think the examples are okay. Please do more exercises that are similar in the textbook. Hopefully you get a better understanding and you can do the exam. So module 10 part 1 is fair game for the exam. Let's go for part 2 now. Sampling theory number 2. We have another 45 minutes. Okay, let's go for another half an hour and conclude our class. A little bit more. Shall we take a break? But we just started 15 minutes. Okay, we can't take a break yet. Okay, so what have we talked about so far? We talked about when we have a sample from a population, how to find the sample mean and how to find the sample standard deviation. And then when we had two populations, each population, we take out a sample, we know what is the sample mean, what is the sample variance, and from another population, we know what is the sample mean and the sample variance, and we know that these both samples, despite from being from two different populations, we know that they are normally distributed. So therefore, we can apply the central limit theorem on them when we are trying to find the difference. Are you seeing the new slide yet or not?
No.
Not. Okay. What about now? Okay. Now, okay, can? Okay. Okay, so everyone is not sounding enthusiastic. Okay, so what have we done so far, right? We talked about finding. We were trying to find the sample mean, and then we wanted to find the probability, and we were estimating what was the sample mean and the sample standard deviation. So in reality, even though we were talking about sampling distribution, we were also doing some sort of point estimation, which is the next part of this class. So when we're talking about data and we want to make an inference or we want to make a conclusion on a data, we call this as statistical inference. When you have a bunch of data on COVID and you want to make an inference, hey, is people being more sick or being less sick? Is the situation getting better? So those are the types of inferences that you would want to see from a data. And this is called the statistical inference. So there are two major areas in making statistical inference, which is parameter estimation, which is what we talked about earlier in part 1 of this module. And another one is called hypothesis testing, which is the next chapter or the next module. We're not going to cover that yet. So an example of a parameter estimation problem is that suppose a structural engineer is analyzing the tensile strength of a component. Since the variability in tensile strength is naturally present, when you have a data, of course, your component will have variability in its tensile strength. That is why we have data. So because of the differences in raw material batches, manufacturing processes, and also measurement procedures. So all of this contribute to the differences in the tensile strength value. The engineer is interested in estimating the mean tensile strength of the component. So what we're doing is we will use a sample data from the population to compute a number that makes some sense, that is a reasonable guess or a reasonable estimation. And this is called the point estimate. So what we're doing just now was called the point estimate. It is a point estimate when we know what is the value. It is a point estimate when we know what is the value or we are estimating a certain value. We have an exact value for that. Okay, continuing on that, what is the difference between estimation and hypothesis testing? Just introduction before we go for hypothesis testing in the future. So estimation is basically taking a random sample from a distribution or a population to elicit some information about the unknown parameter theta. So whenever we are trying to find an unknown, we describe this unknown as a theta. The theta can be the mean, the theta can be the variance, the theta can be the standard deviation, it can be the median. It is any unknown that you want from a data, and that is your theta. So a candidate for public office may wish to estimate the true proportion of voters favoring him by obtaining the opinions from a random sample of 100 eligible voters. So how would you pick the voters to know, to have an accurate estimation for this? How would you pick the voters? Anyone wants to guess? Anyone wants to make a guess? It doesn't have to be perfect. Okay, let's say we have a candidate, right? I am the candidate, the political candidate. And I want to know what is the proportion of voters will vote me. So the true value will be from the population, right? The true value of the votes will be from the total population of Malaysia, let's say. So the whole Malaysia will vote me as the president. Sorry, losing my voice. So the whole Malaysia will vote me as the prime minister, for example. I don't want to be the prime minister, by the way. And to make an estimation of whether I'm going to succeed in this election, I want to take 100 eligible voters as my sample. How should I select this sample? Can I select it from just one district? Is that a fair estimation?
No, you need to take it from multiple regions.
You have to take it from multiple regions, right? For your voters to give you a fair estimation. If you take it from one district and that district is very wealthy, for example, then you wouldn't get a fair estimation of people that will vote you. So same case, if you were to take from a region that is not wealthy, the vote will not give you a true estimation of your total voters from the population. So it has to be balanced somehow. It has to be from multiple regions. It has to be from the wealthy group, the non-wealthy group, and the middle class group for this sample to be good. So we will talk about that later on in unbiased and biased sample. And then hypothesis testing. Hypothesis tests are procedures for making rational decisions about the reality of effects. One is interested in finding out whether or not a new drug is efficacious or effective. He or she conducts a series of drug trials, like our vaccination, and study that if those patients who received the drug or the vaccination did slightly better than those who received a placebo or not. So in this case, we wanted to know, does the vaccine work? Does the COVID-19 vaccine work? So they take 100 people, 50 is given the vaccination, the other 15 is given an injection, but it is a placebo. The injection is empty. And they compare between these two groups, the 50 and the 50, which is highly likely to recover from COVID and which is highly likely to get infected with COVID. So this is how you make the hypothesis testing. And if the group that received the good vaccination or the actual vaccination survives and also do not get infected easily, then you can conclude that the vaccination is effective. So that is your hypothesis testing. You are trying to prove a statement is true. What is the statement? The statement is, does the COVID-19 vaccination work? The answer is based on your data. I don't know. It depends on your data. Okay, but of course it's working for now, right? Okay, so moving on to estimation. We talked about, I gave you an intro on estimation and also hypothesis testing. We're gonna go deeper into estimation and also what can be used as an estimator. Okay, so when discussing inference problems, it is convenient to have a general symbol to represent this parameter of interest. We talked about this. The Greek symbol theta will represent the parameter unknown that you are interested to find. Okay, so this is our unknown. It can be anything that is statistic. What is statistic? Statistic is median, mean, variance, standard deviation, all those parameters. So all of that is called statistics. The objective of point estimation is to select a single number based on a sample data that is the most plausible value for theta. So remember, when we're talking about population, we take a sample from this population and we say, oh, this sample is equal to the mean, blah, blah, blah. The sample mean is equal to the population mean. But what if you had two samples from the same population? Can you just immediately say, oh, the sample mean for mean number 1 is just equal to this population mean, the sample number 2 is equal to the population mean. So you're saying basically that despite taking two different samples from one population, that you would get the same mean? Most of the time, that's not the case. This is, ideally, that would be what we want, right? But most of the time, if we are taking two different samples from one population, the mean is most likely not the same. What we have discussed just now was like the ideal cases of taking one sample from the one population. If we were to take more than one sample, then there would be some difference. So a point estimate of some population parameter theta is a single numerical value of a statistic uppercase theta. This is called uppercase theta. It is also a Greek symbol. The statistic is called the point estimator. So your theta is your unknown or your point estimate. It is a number, and this is point estimate. Whereas your uppercase theta is your point estimator. It's not necessarily a number, and it's typically an equation. So for example, if the population variance is unknown, a point estimator for the sample variance S squared, point estimator for this guy is the sample variance S squared. So what they're trying to say here, if your population variance is unknown, you can actually use the sample variance as your point estimator. It's not the actual value, but it is a point estimator. It's going to be close, but not exactly. And the numerical value S squared is 6.9 calculated from the sample data is called the point estimate. Okay, we don't know what the variance is. We try to estimate based on the sample, right? We have a population, we take a sample, we try to estimate what is the variance. Therefore, we find out what is the variance of the sample, and this is given by S squared. And the point estimate is the point estimate is the value of X squared, which is 6.9. This is just reiterating what we have learned from the previous part in terms of point estimate and point estimator. Don't get confused, it's just the same thing, it's just terms. Okay, they are basically the same thing. So point estimate again is a number, point estimator is the equation. Okay. So in engineering, we often have to estimate the mean of a single population, the variance of a single population, the proportion P of items in a population that belong to a class of interest. This one we are not covering, proportion. The difference in means of two populations, mu1 minus mu2. And then reasonable point estimates of these parameters that we have seen so far are, is that mu is just, the mu for population mean is equal to the mean of the sample. For the population, it is S squared or standard deviation over, variance of the population divided by number of n. And for P, we're not going to cover this one. And then for the difference in mu, it is a difference in the sample mean as well. So those are what we have covered so far. So again, to re-emphasize on this is point estimate is a single value for a population parameter. Now, the one that we talked about was point estimate. There's another way to estimate, which is using intervals. This is going to be covered under confidence interval, which is the third subsection of module 3. The first one that we covered was point estimate. The second one is finding the interval. If we're talking about two samples, and of course, they are going to have different means, what is the interval of this mean? So the interval estimate tells us that. Okay, so moving on estimator. What is the definition for estimator? The point estimator is an unbiased estimator for the parameter theta if the expected value is equal to theta. We have seen this before. Mu of x is equal to mu. We saw this earlier. So if it is unbiased, it will just be equal to the value of the unknown or the true value of the true value. If the estimator is not unbiased, then the difference between the estimator minus the point estimate will be equal to 0 if it is not biased. If it is not biased. So if it is greater than 0 or less than 0, it is called the bias of the estimator. Basically, this equation it tells you whether your point estimator is biased or not. If it is equal to 0, it is not biased. If it is not equal to 0, it is biased. Okay, what is this biased thing? So let's talk about that. So when an estimator is unbiased, the bias is 0. Oh yeah, okay, already found that. So again, remember that estimator is from an equation. And we have several choices for the point of estimator for a parameter. For example, if we wish to estimate the mean of a population, we can consider sample mean, which is what we did earlier, sample median, or maybe the average of the smallest and largest observation in a sample. For example, largest x plus with the smallest x divided by 2. This was one of the ways to find the average, but we didn't use it here. But these are the options that you have for estimator. They are equations that are legit to find the mean. But which one is the best? So to find out which one is the best, we have to use this definition, which is if it is unbiased, it should give us a 0. If it is biased, it would not give us a 0. So let's see. So this one, okay. So I told you if your point estimator, this is hard to write. If your point estimator minus theta is not equal to 0, or it is greater or less than 0, it means that you are basically overestimating or underestimating your theta. For example, my point estimator tells me that the mean should be 5.6. This is based on my point estimator, for example, but the actual mean is 5. My theta is 5. So my point estimator minus the theta will give me 0.6 difference, which means that my point estimator is biased. It is biased in a sense that it is overestimating my mean, which is not good. It is overestimating. So this is called the bias. So let's look at graphs telling us this. If we consider, this is not the graph that I wanted to talk about. Okay, so here we have several graphs. Which estimator is biased, which estimator is non-biased, and which is the best one. We're going to cover this one later. So the mean is given by theta. Which one is biased? Number 3 or number 2? Which one is biased? Remember the definition. The estimator must be, oh my God, this is hard to write. The estimator must be equal to 0. The estimator minus the theta must be equal to 0. Which one is biased?
The third one.
The third one, right? Okay. So let's see why. This one tells us the mean is some value plus, let's just say this is 2. And this is theta. So if I were to find if my point estimator is biased or not, let's say this is the actual value, okay? So this would be theta plus 2, which is some value, minus theta. I would get the difference as 2. And this means that it is biased by overestimation. What about distribution number 2? Distribution number 2 tells me that the point estimator gives me a value of theta. So this would be theta minus theta, which is equal to 0. Therefore, my point estimator is great. It is unbiased because the mean overlaps, even though the variance is different. Even though the variance is different, but their mean overlap, which means that they somehow are centered towards the mean. And we want a data that is centering towards our actual mean because it tells us that our data is roughly okay, right? So that is your bias versus non-bias. Any questions about bias versus non-bias? I'm going to repeat myself here in a bit. Don't worry. Let's go back to the slide. So how do we decide which one is the most efficient estimator? So previously we saw that from the graph, an estimator that is closest to theta would be considered unbiased, right? We want our difference to be 0, and that was unbiased. But if we had several distribution where all of them are unbiased, for example, this is the population, and I have distributions that are all unbiased. See, this is our theta. Oh, this is not it. This is going to be hard for me. Okay, so I have all of this with the same mean. They all have the same mean. They are all unbiased because they are centering at theta. They have the same mean. Which one is the best estimator? Is it going to be 1? Going to be 2? Is it going to be number 3? So this slide tells us this one. If we consider all unbiased estimators of theta, so the orange graph is our estimator. The one with the smallest variance is called the minimum variance unbiased estimator. Let's not try to pronounce this. Let's not try to use this phrase. Let's just call it MVUE. So both are unbiased. So sorry. Look at this graph. We have the first distribution, number 1, and the second distribution, number 2. Our MVUE said the best estimator is the one with the smallest variance. The condition for this definition is that it must be unbiased. If it is biased, the mean is this way, the mean is away from theta, then you cannot use this definition. It would not apply. Oops. So for unbiased estimators, how do you decide between which is the best? Is the one with the smallest variance. This is common sense because we already talked about this since the beginning of class. Smaller variance is always the best because it centers towards the mean. Both are unbiased because they are centered at the true value of theta, yes, but the variances are different. Since estimator number 1 has a smaller variance, then it is more likely to produce an estimate that is close to the true value of theta. So here, the values of this distribution is more closer towards the mean rather than this one. This one is more spread out. Therefore, we would say that the estimator number 1 is the best in this case. Okay. Okay, a little bit more, please bear with me. So again, continuing with the most efficient estimator, this is our definition early on, MVUE. An example of this that we have seen is if x1, x2 up to xn is a random sample size of size n, is a random sample of size n from a normal distribution. So our population is normal with mean, mu, and variance of this one. The sample mean is MVUE for mu. Why? Because this gives us, basically it overlaps with our mu, right? This one was This is the definition of our sample distribution earlier on. So basically they overlap. And the sample mean that we also talked about earlier on has the MVUE, which is the best. Note that the MVUE applies to non-normal population too. Remember, our sample is based on the central limit theorem, and sample that is greater than 30 will always be a normal approximation, and it follows the central limit theorem equation, which is this. And for the standard deviation or the variance, what was it? It was this one over n. Okay, so now let's talk about which estimator is the best one. So just now we already identified which one is biased versus non-biased. What is the condition for MVUE? It has to be unbiased. So what is unbiased here? Only this guy and this guy, but this one is actually the population. We assumed that it was the population, but assume that it's not a population, it is a sample. Sorry, it is a point estimator. And we have another point estimator for this guy. This guy is already out of the question because it is biased. Which one is the best estimator? The one with the smallest variance, which is number 1. And that is it for today's class, I think. Yeah, let's continue this one later. Any questions? So everyone fully understands what we were talking about?
Yes.
Okay. So I'll see you guys later. Bye. Tomorrow.
Thank you,
Doctor.
Doctor.
Bye.
All right, thank you.
Thank you, Doctor.
Have a great rest of the
Thank you,
day.
Doctor.
Don't forget your lunch.
Have a nice day today, Doctor.
Okay, thank you. Bye.
Thank you, Doctor.
Bye-bye. You're welcome. Bye-bye.
Thank you, Doctor.
Welcome.